Hey guys, welcome back. I wanted to spend a little bit of time with you guys today chatting about Newton's second law. So we talked about Newton's first law in the last video, and we talked about how Newton's first law is his law of inertia, which looks at specifically objects undergoing uniform motion. So any object that is undergoing 0 meter per second squared acceleration. So that could be an object at rest, or it could be an object that is traveling at a constant velocity. And specifically when we look at it in terms of dynamics, what we're looking at is the fact that for these objects, the net force acting on that particular object undergoing uniform motion is going to be equal to 0. So all of the forces, when we sum all of those forces together, we're going to end up with an answer of 0 newtons for the net, the resultant force. Now, we also chatted on our very first day in class when we looked at free body diagrams, we chatted about the fact that if an object is undergoing an unequal distribution of forces, or unbalanced forces, if it's experiencing unbalanced forces, then what that tells us is that the object must be accelerating, or it must be undergoing a uniform accelerated motion in the direction of the imbalance. So I demoed that for you guys with the pulley system, where we had the 200 gram mass and the 100 gram mass, and we were able to show that since the force of gravity on the 200 gram mass was larger than the force of gravity on the 100 gram mass, that meant that the entire system was going to accelerate toward the 200 gram mass, because that was the direction of the imbalance when we set up our free body diagram. So Newton's second law, basically the most common way to express Newton's second law is force net equals mass times acceleration. That's kind of the known Newton's second law, and that's the formula for Newton's second law. Essentially what it says is the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the net force. So inversely proportional. So that means that if the mass goes up, the acceleration is going to go down, right? Because it's going to require a larger net force to get it accelerating. And so what we're looking at is that imbalance in the forces of the overall object. So I've got an example here for you, and this is actually very similar to the example of the hockey puck that we did together in class, where we've got an unbalanced system of forces here in the horizontal direction. And so just by looking at this, because I can see that my force applied is so much larger in magnitude than my force of friction, I know that this object must be accelerating toward the right. So in this case, I know that my net force is not going to equal 0. There's actually going to be a net force that is showing a direction that is equal to the direction of the larger, or of the imbalance, the larger force, I guess. So in the vertical direction, that's what I've summarized for you guys here. In the vertical direction, we know that this object it's not going up or it's not going down, because these forces are equal and opposite. So in the vertical direction, we're at a uniform motion because there's no acceleration. But in the horizontal direction, we know that for sure that there must be an imbalance in the forces, which means that F net cannot equal to 0. And if F net cannot equal 0, then that means that we must have an acceleration on this object. So even in, and let me just jump back here for a second, even in Newton's first law, this is still valid. Force net equals ma. That's always valid. The thing is that in Newton's first law, because acceleration is 0, regardless of the mass of the object and all of that, the net force is always going to equal 0, because A equals 0, right? So if we go to an example here with our hockey stick, so we have hockey stick applies a force, really it's the hockey player that applies a force of 7.5 newtons on a hockey puck that weighs 0.170 kilograms. We want to determine the acceleration of the puck, right? And we're going to assume that there's no friction from the ice. You know, for all intents and purposes, there is a little bit of friction, but it's really quite minimal. So we're making the assumption that there's no friction here. So in terms of my free body diagram, I know that the hockey stick is actively pushing on my puck, so there is a force applied on my puck. In the vertical direction, I've got my force normal because the puck is sitting on the ice, so that's a contact force from the surface, and there's gravity that's pulling the puck down. Now in my y direction, in my vertical direction, I know that the net force is equal to 0. So I'm just going to make a quick statement here just to show that I know that in the y direction there's nothing happening in terms of motion, or acceleration is equal to 0 meters per second squared. So F net is equal to the sum of the forces, and that's equal to 0 newtons. And I'm just going to leave it at that for the y direction. I'm just making the statement to show that I know that there's nothing of importance happening in this direction at the moment. In the x direction though, if I sum my forces, I know that if I look at this, there is definitely an imbalance in the vectors in the horizontal, because I've got a force applied, but there's nothing balancing that force applied on the left-hand side. So in this instance, I know that force net cannot equal 0. And if force net is not equal to 0, then that means that I have to restate this F net as mass times acceleration. And I'm going to sum all of my forces in the horizontal, and my only force in the horizontal is F applied. In the question, they told me that the mass of the hockey puck was 0.170 kilograms, and they told me that we applied a 7.5 Newton force, and we want to figure out what's the acceleration. So for this hockey puck, the acceleration is 44 meters per second squared, which is the actual average acceleration for a slap shot in hockey, for your information. So that's typically what would be happening when, you know, your average player goes and takes a slap shot. So that's a Newton's second law problem. And the second law we know because force net is not equal to 0. So we know that we have to insert this mass times acceleration here because there must be some acceleration that this particular object is undergoing. A second example here, where we're going to take into account some components, so slightly more complex. We have a 20 kilogram box that is pushed with a force of 60 newtons at an angle of 45 degrees below the horizontal. We want to know if there is a force of friction equal to 10.0 newtons. We want to find the acceleration of the box and the net force. So we've got a diagram here for this particular question. We know that we've got a person pushing on this box. We know that they're applying a force at an angle of 45 degrees below the horizontal. So that's the angle right there. And I'm going to draw my free body diagram. So this diagram that I've drawn here on the left, this is officially my free body diagram. This is specifically what you must show on a long answer problem. So I know that for this object, I know that there's a force applied being applied by the person pushing down on the box at this angle of 45 degrees to the horizontal. That's my force applied. I know there is a force of gravity, so gravity is pushing down on the box, and I know that the ground is returning that force in terms of a contact force. So I know there is a force normal. And they did tell me there was a friction force. And because the object is being pushed here to the right, that means the friction force must be to the left, since friction always opposes the direction of motion. Now what you might notice is, and you would correctly surmise, the box is not going to be moving through the floor or levitating up off the floor, right? So that means that the forces here in the y direction must be equal and opposite. But you might notice that when I drew my force normal, this force normal is quite a bit longer than this force gravity, which means the force normal is larger in magnitude than the force gravity. So how can these forces be balanced if this force normal is so much larger? Well, what's happening specifically is that because this applied force is being applied at this angle of 45 degrees, this applied force actually has a horizontal component and a vertical component. And what I've drawn here, and this is kind of a web kind of thing that I like you to do because it shows you specifically what all the forces are that are pulling together. What I've done here is I'm showing that I have a force applied in the parallel direction. I have a parallel to the surface. I have a force applied in the perpendicular direction, perpendicular to the surface. And really what's happening, because I have this perpendicular force from the force applied in the downward direction, the reason this force normal is so large is because the sum of force gravity and force applied perpendicular, the sum of these two vectors is equal to the magnitude of the force normal, and it's pointing in the opposite direction, right? So that's why this vertical component has a net force of 0, which I've stated here. So force net is equal to 0 in this vertical component in the y direction. In the x direction, however, in the x direction, I know that my forces are not balanced because, you know, they're telling me find the acceleration and find what the net force is. I'm not moving at a constant rate. So in the x direction, I know that F net x is equal to the sum of the forces x. I know that because F net in the x direction is not equal to 0, I need to restate this as mass times acceleration. And then if I sum the forces in the x direction, I have my force applied, and I have my force of friction. Now the force applied isn't this, you know, vector here that's applied at the 45-degree angle. The force applied is the cosine of the 45 degrees times the 60 newtons from the original, you know, pushing here the question being. And so that's why I like showing this particular setup here, because now I can see that it's the force applied parallel to the surface plus the force of friction. So if I come back down here, force applied is equal to force applied. Oh, sorry, I should restate this. This is slightly off. It's equal to force applied parallel times force friction, and the force applied parallel is equal to force applied times cos theta plus force friction. So now I'm going to insert my values. Well, they told me the box had a 20 kilogram mass. I'm looking for acceleration. I know that the force that the person was applying on the box is 60 newtons. I know the angle was 45, and I know the force of friction is 10 newtons, but it's in the opposite direction, which I'm saying is negative. And so if I rearrange and I solve for acceleration, I got positive 1.6 meters per second squared to the right, because it's positive, right? Now if I want to figure out net force, well, the net force is equal to mass times acceleration. So 20 kilograms times 1.6 meters per second squared. And that tells me that my net force is 32 newtons to the right. Right, so that's why there's an acceleration to the right, because there's an imbalance of 32 newtons to the right. Now that third type of question you might see is what we call a bird's eye problem. And the bird's eye problem is almost like you're watching this particular example happen from above. You've got a bird's eye view, right? So they're telling us we've got a 20 kilogram toboggan. It's being pulled out of a snowdrift, and the snow opposes the pulling with a force of 8 newtons. We want to find what is the acceleration of the toboggan if one person pulls with a force of 15 newtons at an angle of 20 degrees, and the other person pulls at 20 newtons at an angle of 30 degrees. So here's our scenario. This is our toboggan here. Our force friction, or its opposing force, is pointing away from the direction that the people are pulling. I've got a force from the first person pulling. I've got a force from the second person pulling, which I'm calling F1 and F2. My first person is pulling at an angle of 30 degrees to the, the vertical or the horizontal here. My second person is pulling at an angle of 20 degrees. Okay. Now, because these forces are being applied at an angle, that means that these forces are going to have components, right? And so if I break this free body diagram into the individual components that are acting in that horizontal and that vertical direction, what I get is that on this horizontal, there's going to be a parallel component to my first force and a parallel component to my second force, which I'm showing here. And there's going to be a perpendicular component to my first force and a perpendicular component to my second force, which I'm showing here. Okay. And you'll notice that because the magnitude of this force applied is 20 newtons and the magnitude of this force applied is 15, you'll notice that my force perpendicular here, the first one, is going to be slightly longer than the perpendicular force from the second person. And then the same thing here, parallel here. And the same thing here with the perpendicular forces. The perpendicular force is going to be slightly longer than the perpendicular force from the second person. So you're trying to as best as possible keep track of the magnitudes of these particular vectors, because it is important, and when you're doing a long answer problem, you have to make sure you take that into account. So much like we did in the kinematics unit, we're going to set up our components. So we have the parallel. The reason I'm using the parallel and the perpendicular is because in the Pearson textbook, that's the format that they use. And so the parallel is the horizontal, the perpendicular is the vertical. So in this case, here's my first force applied at an angle of 30 degrees. Here's my parallel, here's my perpendicular. So in order to solve for the parallel component, this is adjacent, right? So I'm solving, it's 17.3205 newtons, positive because I'm saying right is positive. The perpendicular is the opposite to the 30 newtons. So I set up my equation here and I get positive 10 newtons. Now I'm not going into too much detail there because we talked about this particular setup quite a bit in kinematics. For my second force was in this direction at an angle of 20 degrees. And if I'm looking for the parallel, which is that horizontal, the parallel is adjacent, so cosine. Perpendicular is opposite, so sine. So I set up my equations, I get 14.0953 newtons. In this case, right is positive, so this is positive 14. Down is negative, so this is negative 5. And I have to manually insert those signs. And then the third vector is my friction force, which is acting on the horizontal or the parallel, right? So they told me my friction force opposed at 8 newtons, which means negative 8 newtons. And then in the vertical direction, there's nothing happening, so it's 0. Now, same rules applies with kinematics. The net force is my resultant force. So what I'm going to do is I'm going to take the sum of the 17, the 14, and the negative 8, and I get positive 23.4 and change newtons. I'm going to do the same thing here with the perpendicular components, and I get positive 4.8 newtons. And so what that tells me is that the horizontal component of the force net is 23.4 newtons in the positive direction, so it has to be pointing right. And the vertical component of the force net is positive 4.8, which means that this vector has to be pointing up. And so that will give me my right angle triangle so that I can use my Pythagoras theorem. So F net squared is equal to F parallel squared plus F perpendicular squared. I'll sub in my numbers, solve for F net, and I get 24 newtons is the magnitude of this net force. Last thing I have to do is I have to solve for the angle. Okay, so the angle is opposite for this angle here is opposite over adjacent. So my perpendicular force and my parallel force, and I get 12 degrees. which means that my net force when I pull up the toboggan, it's going to be moving in this east 12 degrees north direction, and it'll be coming out with a force of 24 newtons. The second part says, well, if the toboggan has a mass of 20 kilograms, what is the acceleration? So I know the net force is 24 newtons. I know the mass is 20 kilograms. My acceleration is 1.2 meters per second squared at this direction, east 12 degrees north. So that's a bird's eye problem. Another type of problem you can see is something like this. We have a person that pushes on a box with a force of 20 newtons. If the mass doubles and the acceleration decreases by a quarter, how does that affect force applied? Okay, so I know force net. They told me the force net is 20 newtons, and that's equal to mass times acceleration. If I double my mass and I quarter my acceleration, that means that force net is equal to 1/2 times mass times acceleration. And so that means that if I were to do that, double the mass and quarter the acceleration, this mass times acceleration would be halved because I'm multiplying by half. So in that case, my force net would be half as large as it was originally. So it would be 10 newtons. So those are kind of the three types of example problems that you would kind of encounter and what we're going to be practicing during class time. So I know there's a lot of stuff there. If you guys have questions, let me know during class time. We'll practice together, and hopefully you'll get the kind of the setup under your belts. But you know that the setup is always the same as it was when we talked about first law. Sum all of the forces in that horizontal direction or in that vertical direction. And in second law, force net is equal to mass times acceleration. In first law, force net is equal to 0 newtons. Okay, so we'll leave it there. I hope you guys are doing well. Let me know if you have any problems, and we'll chat soon. Take care.